we're studying logarithms, or sorry, exponentials and logarithms. And so I wanted to go through some helpful examples that are based on what we have in the textbook, and move on to first for exponential functions, and then do it for also start the section on logarithms. Okay, let me just check it. Okay, good. Stream health seems to be fine. Okay, so the last time I introduced the exponential functions. Here the typical exponential functions are shown in the diagram that I wrote last time. Let me just erase some other stuff. All this stuff here was talking about calculating exponential functions for rational numbers first, and then that's in order to approximate a real value for an exponential function. So let's just go back to that function. So the exponential function is y is equal to b to the x. So that's a basic, I call it a basic exponential function. And b could be, usual case will be b is greater than 1, or we could also have b is between 0 and 1. So I've illustrated the two cases here. In both cases, yeah, we have they should look symmetrical. I'm not doing exact. I'm not plotting exact points here, but they should look symmetrical like that. This goes up very quickly, and yeah, still doesn't quite look right, but now. They go through the same point at x equals 0, namely y is equal to 1. So that's the same point 0. And there's a characteristic value or a special point at x equals 1, namely you get the value b, the value of the base. So for this one, b greater than 1, we have b greater than 1. For b less than 1, here, another value of b goes in there. Let's call it b prime. So this will be the value of b prime. Okay. All right, so hopefully that's clear what I mean by the basic exponential function. Now we'll have another more general variety of functions. Just take the old basic exponential function and multiply it by a constant in front. Okay, so whereas we have the same restrictions on b here, b is greater than 1 or b is between 0 and 1, the restrictions on a are much more, are less. So a is any real number. And in order to restrict ourselves away from, just getting a simple 0 function, a should be taken to be non-zero. But a can be positive valued or negative valued. Okay, so what this results in, when you multiply by a, is you get a stretching of the graph or possibly compression of the graph in the vertical direction, in the y direction. Okay, so then this simple graph becomes let's say, starting here, for b greater than 1, we'll get a graph which looks like this. Okay, and this intersection point will be A. So when you plug in x equals 0, this part becomes 1, and now you just get y equals A. And then for b prime less than 1, it'll look like this. Again, both graphs will go through this point 0a. And if I want to find a characteristic value here at 1, I will get, if I plug in 1, a times b. Right? This part will evaluate to b, and this will be multiplied by the overall constant a. So this point here will be a times b. This point here will be a times b prime. Okay. So this is a more general form for the exponential function, which the book adopts. And so let's see some examples. We'll also deal with the shifts and stretches of this, both in the horizontal direction and in the vertical direction. We can have both shifts in the horizontal direction and shifts in the vertical direction, as well as stretches or in the horizontal direction. And then this we see is already a stretch or a compression in the vertical direction. Okay, so I'm just saying we can have all the varieties of transformations that we looked at we saw in chapter 3 here as well. And I would mention, first I want to mention a couple of things. These graphs they always should be smooth. I'm trying to draw them smooth. That means without corners. One graph at a time just goes right up without any abrupt changes. And so that's all the real numbers have some value associated with it. That's what I was saying before. So to get a value at an irrational number here, you can approximate it by values that are close by. And we're assuming or depending upon this fact that the graph is indeed smooth. Okay, another thing that I wanted to mention. So that's a note. Graphs are smooth, meaning continuous, no corners, no abrupt changes. On the range. And two, a note is that we can have stretches and shrinks, or stretches and compressions. In both vertical, as I have here, and the horizontal directions. with some, I just want to say that the vertical stretches and shrinks here they lead to different graphs here that they're kind of new compared to the original unstretched basic exponential function. However, we'll see that stretches or shrinks in the x direction, in the horizontal direction, are also sort of achievable by choosing a different b. Okay. So stretches or shrinks in the x direction actually correspond to choosing a different base. And we'll see this also for logarithm functions. It has a similar property. The logarithm functions will be the inverse functions of the basic of the general exponential functions. And we can also have shifts in both directions. So vertical shifts are obtained by adding a constant d to the overall function. Right, I could call these f of x here. Instead, I'm just calling them y equals that. But anyway, a vertical shift will again produce a different function than any of these forms so far given. Okay. I'm saying down here that you don't get, by doing a horizontal stretch or compression, you don't actually get a new kind of function than this one. Here, when you do a vertical stretch or compression, you have to write down a new form, different from this. But if you just do a horizontal compression or shift, then you can just use the same form here, just modify it with a different b. Okay. Now, for vertical shifts, again, you get, when you add a d to this, you cannot somehow make this into the old form abx. You have a new form for the function. So the whole thing gets shifted up or down sort of uniformly. And that means this asymptote here, y equals 0, the horizontal asymptote, there's no vertical asymptotes in these situations, but the horizontal asymptote gets shifted up or down to y equals d. Depending on whether b is positive or greater than 1 or less than 1, that asymptote will be where the curve tends to for x going to plus infinity or x goes to minus infinity. Okay. Now for horizontal shifts, again, we'll see that if you start with this curve here and you do a horizontal shift, it will correspond to keeping the base the same, but changing the overall factor of a. Okay, so that's a note that I wanted to bring to your attention. Okay, so horizontal shifts which will lead to new functions of this form. So after you do this one, let's say you come up with this form here. This will be a horizontal shift in the x direction of c units to the right. The book uses a plus here, but I prefer to use a minus because it's the it's our intuition. Our intuition says that you want to increase to the right. So if you shift to the right, then you have to subtract the constant here. So the horizontal shift, this corresponds to simply a new a prime, where you can use the old bx without any shifting. And likewise, the d stays the same. Okay, so let's see what these graphs will typically look like when you do shifting and stretching in the vertical and horizontal directions. Okay, so basically the book has this as the most general form with a plus sign here. But what I'm saying is that the most general form can actually be written as this. For arbitrary shifts and stretches in the vertical and horizontal directions. Okay. We'll also see that reflections can be represented by a change in the signs of, here in this case it would be overall change in sign for A and D. And that's a flip, that will flip the graph about the x-axis. So positive y values become negative y values. Okay. And if you want to do a reflection in the y-axis, so positive x values become negative x values and vice versa. That will again change the sign of x here will also change the sign of, will change the value of b. As we saw before, b will, when you flip about the x-axis, it corresponds to changing from b to 1 over b. So the value of base, that becomes, so I'll just write these down. So reflections about the y-axis. So this graph goes to minus a bx. So the whole thing gets multiplied by a minus sign. Minus a times b to the x minus d. And about the x-axis, so this is the same form as we had before, just a different a and a different d. About the x-axis, it will be obtained by putting a minus in front of the x. And this is now a new base, namely so this can be written as a times 1 over b to the plus x plus d. Okay, so I'm trying to clarify that we have all these operations that we can do to functions: shifting, stretching, vertical and horizontal directions and reflecting in both vertical and horizontal axes. This is reflecting about the horizontal axis, this is reflecting about the vertical axis, the y-axis. Sorry. Yeah, sorry, this should have been x-axis, this should have been y-axis. Okay. But they correspond to simple changes of these parameters in both cases. All right, so I'm just trying to kind of summarize what the book has, and we'll see this in examples. We already saw this in one of the first examples we had last time. Okay, so let's try some try-it exercises here in the textbook. This is try-it number 1. This is section 6.1. By the way, if you haven't already done it, try practice the practice test for chapter 5. Okay, it's at the very end of chapter 5. That will help to get a good handle, good grip of the material in chapter 5. All right. So let's do try-it number 1. These are quite easy at first. Which of the following equations represent exponential functions? So I'll just write them down. Okay, so this is obviously a quadratic, namely a polynomial, 2x squared minus 3x plus 1. I'll just write them all down first. And we have 0.875 to the power x. H of x is 1.75 x plus 2. And j of x is 1.1095.6. It's all one number to the minus 2x. Okay, so now remember, another thing, order of operations is important. Remember, you always do the exponentials or you always do the exponentials first, raising things to a power first. Then you multiply and divide, and then you add and subtract. So the order of operations is first you evaluate this, b to the x, then you evaluate 8 times that, and then you add the constant d if there isn't. Okay, so, and now the exponential, the quadratic function here, is there a way of writing it as an exponential function? Okay, the answer is no. You cannot find a base b, an a, and a d such that a polynomial will equal the exponential function. You never can. The reason is that for very large x, this behavior will always be much greater than the highest power behavior of a polynomial. No matter how high this will be some fixed leading power. The degree was always some finite number. Okay, and that will always be out, beaten by an exponential one. Exponential growth is always bigger than the polynomial growth. So this is not, and never can be expressed as an exponential function. This is already in the exponential function form. We have a base b is 0.875. It's the simple or basic exponential function I wrote down. So it is. This is linear. So again, it's like the quadratic. It's not going to be expressed as an exponential function, so it's not going to work. And this is, j is given, and the base is given here, and it's something very large, 1095.6. And then we have this minus 2x. Okay, and that's going to be this is going to be actually of this simple exponential form, where I don't have this same thing as a base b yet, but the base b will be something else. But at least it will be of this form where I've either shrunk or stretched one of these basic exponential forms. So this will be an exponential function. What will be the base, by the way? What will be the new base if I incorporate this minus 2x? It will be b prime is equal to, will be 109 5.6 to the power minus 2. How do I know that? Okay. Well, I use some of the basic properties that hopefully you've seen before for exponentials. Remember, if you take a number and raise it to the power b, and then you take that and raise to the power c. Okay, so there's a basic rule that you take the same base as before that you started with before you raise it to the power b. Then you take that as a new base and you raise that to the power c, right? So you can do the whole operation by starting with a, this original base, and raising it to the power b times c. So you do the b times c first, and then you evaluate the exponential. Okay, so that I can use in reverse to write this function. In exponent, I have minus 2 times x, and I can write it as a b. The b could be minus 2 here, and I can leave the c as the x. So if I group this, first raise this base to this power minus 2 first, and then raise to the power x, then I'll get the same thing. That's what this rule says. Okay, so that now I've shown that I can represent this as a basic exponential function with the new base b prime, which is this. Okay. So that's just a matter of using some of the rules of exponential and logarithm functions, which we'll get to later in more detail. All right, so now evaluating exponential functions. This is try number 2. In section 6.1. I'm sorry, I did try number 3 rather. Okay, let's see. So this has to do now with population growth. So exponential functions are basically the only way, or they were kind of invented in order to describe growth of populations, and they're used heavily in that topic. All right, it's basically saying that the larger the population is, the more it will tend to grow. If you assume that a certain percentage of the population is reproducing, okay, then that's probably constant in all of society. So the larger there is a population, then the more families you have, the more children you have. Okay, so there's a certain percentage of the population which will be reproducing, and then that will tend to make the population grow over time. Now the way the way you describe this population growth is that you have a certain percent increase per year or something like that, per time period. Okay, so population growth is expressed as a percent change per time period. Okay. Now think about linear functions, which you studied before. In linear functions, you have a slope. You have a straight line graph, so you have a constant slope. What that means is you have y is equal to mx plus b, let's say. Okay, y-intercept is b, the slope is for change of 1 in the x direction, you have a change of m in the y direction. So the ratio is always the same. And here I've shown that slope by choosing delta x as 1, and then delta y as m. All right, so in a linear function, for a given change of x, for a fixed change in x, change in y is constant. So it doesn't matter where along the x-axis the change is made. Here I've shown a change over here, but I could have easily shown the change to be over here, and I would have gotten the same change in y here, in the m. Okay, so you could shift this little triangle anywhere along the straight line, and it will represent the slope of the straight line anywhere. Okay, but now for exponential functions, this change or shift in x will correspond not to an addition to y, right? This is a difference of y values. So it corresponds to adding m to y1 to get y2. Okay, but here, in the exponential case, you have, instead of a shift, you have a stretch. Okay, a stretch in the y direction. So if delta x is x2 minus x1, then you don't get a delta y. You get a, well, you do, and you can consider delta y, but the characterizing feature of an exponential function is that not that there is no constant shift in the y direction for a given shift in x, but there is a constant factor that you have to multiply by. So y2 divided by y1 is going to be a constant. Okay, so let's see that. That's for a basic exponential function. Actually, for one without a shift in the vertical direction. So it's not quite so basic. It's with the extra factor of a here. Okay. So if I increase x by delta x, by some fixed value, constant delta x, then the new y prime So so we start off, let's say, at x1. And therefore you get y1. Then to get y2, you add your constant change to x1. That will give you x2. Okay, but now this, when you add to the exponent for a fixed base, remember what that does. That corresponds to taking the base raised to the power x1 times the base raised to the power delta x. So again, we'll use one of our rules for exponentials, which we'll see later. And we'll see this is all raised to the power b to the delta x. Okay, so the b can come out front. So it's basically showing that b delta x is b delta x times y1. This is the original y1. Okay, so it corresponds to an actual factor multiplying y1. When I add a shift to x1, it corresponds to a stretch in the y direction. Okay, so, and I think I mentioned that before. Remember that I mentioned that a shift in the x direction, like this, corresponds to a new a prime, like this. And you can go both ways. You can go to a pure shift in the x direction just by taking appropriate value of c, so that a, right, this is equal to a bx times b to the minus c. Let's just choose this whole thing to be 1. I'm sorry. Let's choose this whole thing to be a new value of c, namely c prime. And then this whole thing will become b times x minus c prime. The whole function can be described in that way. All right, so in the end then, a vertical stretch or shift or compression corresponds to a horizontal shift. So that's something I've talked about before actually today. All right, so that's what's going on here. Okay, so that's why an exponential function, for a linear function you'll have a constant slope. Polynomial functions you'll have some growth, but this will beat any growth exhibited by any polynomial. Okay. For polynomial growth, for simple power law growth, multiplying by a certain factor of x, multiplying x by a certain factor, okay, if I multiply x by some constant k, then y is multiplied by what? If you put the x in, the k in with the x, and then raise to the power n, then that will be k to the n by the rules for, okay, again, these are rules for raising something to a power. You get k to the n times x to the n. So y is then multiplied by this factor from the original function. Okay, but that's only for polynomials. That you only get this new factor for y. You have to multiply the old y to get the new y. You have to multiply this factor to get from the old y to the new y, right? And for polynomial growth, or this power law behavior growth, you can only do that by multiplying x by a factor. But for exponentials, you can do that by shifting x, which is a lot less, right? A lot less growth. It's just in fixed time you would constantly be multiplying. Each time you go one step, you multiply y by the same factor. You go another step, multiply y by the same factor. For polynomial growth, you have to multiply x by those factors in order to get the change of, in order to change y by those same factors. Okay, so this results in much quicker growth than any polynomial growth. Okay. So now, as a practical example, they consider the population of China, or also the population of India. So, population growth. I'm going to try at number 3. The population of China is about, this is my sign for approximation, 1.39 billion in 2013. With an annual growth rate of 0.6%. Okay, so to describe what that means, you'd say every year the population increases by 0.6%. All right, so you would start with the original population, and then you would take well, it always deals with E. So I would have to explain this a little bit. Generally speaking, when you're talking about annual growth rate that is expressed as a percentage like this, then you can write it as in terms of the natural exponential, base E exponential like this, where I take the rate. Now this should be expressed as a decimal, 0.006. Okay, this is less than 1%, so it's going to be less than, it's 6 thousandths, 6 over 1,000. All right, so you write this rate in, and then you multiply by the time. So this will tell you in 1 year how much growth there was. Actually, let's see. Let's be careful here. Okay, sorry. This should be, yeah. Sorry, this is what I need. Sorry, that's for continuous growth. I should be careful about using E. So for simple for annual growth rate, so after 1 year, if you put in t equals 1, well, first if you put in t equals 0, this part is 1, and I just get 1.39. So that's my starting growth rate, 1.39 billion. That's in 2013. So then in 1 year, this will be 1.06 times 1.39. What is that? We just have to multiply that out. So you just take 0.6% of the original population and add it to the starting population. Okay, so let's just see what that is. 0.006 times 1.39. You have 6 times 9, 54. 3 times 6, 18. Add the 5 is 23. 1 times 6, 8. Add the 2. And I have how many decimal places? 5. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And then I add that to the original population, so it's 1.39. So in year 1, I get something like 1.398. If I just stop at three significant figures, which are these ones, or 2 decimal places, then I'll get 1.40. All right, and also if you do it one more time, if you try t equals 2, then you just multiply that new number by 1.006. I can get this number by simply multiplying by 1.006. Do it again. In other words, take 1.006 squared and then multiply by 1.3. 1.39, and then I'll get something bigger, maybe 1.41. Okay, if you have a very small number here, then doing this operation, squaring, cubing, for a while it will actually look linear. It will look roughly linear. If you check out using a calculator, it's just because the graph is increasing very gradually here. But it's because the base is very close to 1. Okay. If it's equal to 1, then you just get the constant straight line right through like this. But this has a gradual slope, but eventually it will go very quickly off to infinity. Okay. So these are just some examples. Excuse me. If you look at this example as well as the starting example number 3, they have the population of India. So the population of India is estimated as 1.2% per year. And so at that rate, you can calculate that will be a faster rate. So the population of India will eventually catch up to the population of China if it keeps going. If they both keep going at that rate, and will overtake it. And so, yeah, these models are they're good for certain periods of time, but of course they probably won't be appropriate for an extremely long time. They'd have to be modified, with other factors. Okay, so population of bacteria is another example which is dealt with in the textbook. So this is an important practical application of the exponential functions. Growth of bacteria. So these are population growth. Bacteria population growth. As well as radioactive decay. Radioactive decay is those are given by examples where you have a b less than 1 or you have a change of sign in the exponent. B could be greater than 1, as we saw before, but if you have a minus sign there, then that leads to an exponential decay like that. So it's just a reflection of the original exponential growth case about the y-axis. Okay, so radioactive decay works according to such laws. All right. So let's evaluate certain exponential functions and see what we get. Okay, try number 2. I skipped that one, but I think I did actually do it here. Compared it as an example. So try number 2. Okay, so what this is dealing with is you're given values of the function. Oh, sorry, you're just asked to evaluate this. Yeah. So f of x is equal to, you're given this function 8 times 1.2 to the x minus 5. So this is the simple multiplication here. And evaluate f of 3. And they suggest using a calculator. Well, we are mathematicians here, so we are calculators. And so we'll just do it ourselves. Besides, I don't have a calculator readily available. I do actually have Maple, but it's like using a sledgehammer to crack open a peanut. Okay. Well, as it turns out, this calculation is not too hard. All right, so let's try it then using simply plugging in. The good old-fashioned plug-in method. Okay, so F3 plugs into where you see the x here is equal to, so f of 3 is then equal to 8 times 1.2, 3 minus 5. Okay, so this graph looks like roughly something like this. It's got a base b which is bigger than 1, so we'll make note of that. It's got an extra factor in front, a. Right. B is equal to 1.2, greater than 1. So it will be an increasing function like this. And with this shift here, okay, we don't quite know what x is, what the value of y is at x equals 0. We'll plug it in. I mean, if you plug it in, you can get that. By the way, that shows that the exponential functions always have a y-intercept, but never have an x-intercept, the simple ones at least. So a bx only has a y-intercept. And remember, it only has one because it's a function. You always get the y-intercept by plugging in x equals 0. And if it's a function, there's only one y value which results as output. Okay, so here's our function 3, plug in x equals 3, and you get this value, which now you can evaluate using the rules for exponential. So 1.2, 3 minus 5, you simply do subtraction, minus 2. Now this is a negative exponent, so that means you raise this to the power 2, and then you take the reciprocal. Okay, so what's the square of 1.2? It's 1.44. 12 squared is 144, and then you have 2 decimal places because you're multiplying these two numbers. One by itself, same one by itself. Okay, and now you have 8 divided by 144. Well, we can do some simplification here. This is 800 over 144. This is divisible by 16. Check that. And you get 9 here, and then this would be Divide by 8 and you get 100, divide by 2 more and you get 50 up here. Okay, so it's 50 over 9, and you can easily verify that 50 over 9 is just a decimal, 5.556, rounded off to 3 decimal places. Actually, they asked for 4, so it's 5 repeated anyway. So even without a calculator, it's not too hard to get this. All right. And that's approximate to 4 decimal places. If I round up, if the last digit after this is 5 or above, which it is. Okay, so another problem is given 2 points. I'm going to try 4. Given 2 points on one of these exponential curves, find the A and B. So we're given this form, a times b to the power x. And we're told that these 2 points are on the graph. -2, 6, and 2, 1. Okay, so find the original form of the function. In other words, find a and b for the original function. Okay, so to do this, you simply plug in these points into the original function. This is y. Appropriately, so this is x, this is one pair of points, this is the x value, this is the y value. So I plug x into here, and so for the first equation I get 6, which is y, is equal to a times b to the x is minus 2. So that's one equation. I call it 1. And the second point tells you plug in x into here, and you get, as a result, y is equal to 1. So 1 is equal to a times b to the 2, b squared. So that's equation 2. Now I want to solve for both a and b. Okay, so one way I can see, so these are not linear equations. So you might have, you had experience solving systems of linear equations, 2 equations and 2 unknowns, for example. But these are not linear. These are not linear equations. But there's still simple ways of solving these equations. Here you notice I have a factor of a in both of these expressions. And you use the rules for combining equations or keeping equations equivalent, operations on equations, which will keep them still equations, true or not true, as the case may be. So I can perform those operations. And so a simple division of one equation by the other, or this side by this side. Okay, let's see what that does. That's what I'm going to try here. So I can see when I do that here, I just get 6. 6 divided by 1 is 6 here. And over here, I get a times b to the minus 2 over a times b squared. Now the nice thing here is that this unknown a cancels completely from this equation, and I just get an equation in terms of b and a numerical constant. So I can solve this for b in principle. And here it's not too hard, as we can see. You get 6 is equal to, and I combine the powers here. So this is minus 2, minus 2, right? So this becomes a negative exponent in the numerator, and then I add the exponents by when I multiply the two, and I get minus b to the minus 4. Okay, notice this is a 6, not a b. Okay, so then I solve for b, so what do I do? So I can, this is a 1 over b to the 4th, so I can put this, take the reciprocal of both sides and put the b 4th over here. The b 4th is 1 over 6, and I can take the 4th root of both sides. So I get b is 1 over the 4th root of 6. And the book gives this, let's see, this is one of the examples, actually. This is an actual example, not a triad. So the book gives this as an example 0.6389 when you evaluate it. So that's the value of b. How do you get the value of a? Well, you just back substitute, right, your value of b that you found into one of these two equations, and then you can solve for a. And what you get is, let's do this exactly and round off later. Okay, so using this formula then, b 4th is 1 over 6. So b squared, right? So just check that b squared is the square root of both sides. You get if you take the square root of both sides, you get b squared is equal to 1 over the square root of 6. Okay, so if I solve this equation, first equation, for a, by plugging in b, I get, okay, sorry, the other one was, maybe it was appropriate. Well, either one should give you the same answer. But b minus 2, b to the minus 2 is 1 over that, which is root 6. Simply. Now when I divide both sides by square root of 6, I get 6 over root 6, which is just the square root of 6, because that's the square of this. All right. So that's the exact answer for A. And that's about 2.4492. All right, let's do their try it question. That was an example. So try it number 5. Let's do that one. All right, so this is you're given 1.3, sorry, 1, 3, and 2, 4.5 are the points on the graph. Find A and B. So let's see how it works. So here's our form, 8 times b to the x. Plug in values. You get, for the first equation, 3 is equal to a times b. That's equation 1. For the second equation, you get 4.5 is equal to a times b squared. Okay. So now there are two ways to solve this. So I could do it as before. I can divide. It's easier now to divide equation 2 by equation 1. There are other ways to solve it. You can say first square number 1, and then divide that by number 2. Then you'll cancel the b's, right? Because when you square, you'll get a b squared here. And you'll only get a squared divided by a, which will give you a. So that's a way of solving for a directly. But it doesn't matter which way. The first way I'm going to do is just going to give you b first, and then you can always go back and solve for a. So if I divide 2 by 1, I get 4.5 over 3 on the left side, and a times b squared over a times b on the right side. The a's will cancel, the factors of b will cancel, I'll get just b. And on this side I get 4.5 over 3 is 1.5. Okay, so I found my b. b is 1.5. Okay, so now I plug b in here, and I get 3 is equal to 8 times 1.5. And so a is equal to 3 over 1.5, and that's just 2. So here are my two parameters, a and b. So the original function is just, therefore, 2 times 1.5 to the power x. This is a decimal, this is a multiplication. You can also be clear by just writing this whole thing out like this. So that means do this exponentiation first and then do the multiplication. Okay, one can check that this gives you the correct answer. If I plug in x, I get 1.5. X equals 1. Sorry, I get 1.5 times 2 is 3. That's correct. If I plug in 2 here, uh-oh, something's wrong. Oh no, that's fine. Yeah. If I plug in x equals 2, then I get 2 times 1.5 squared. 2 times, so 1.5 squared is, you can check that's equal to 2.25. And I double that and I get 4.5, so that's fine. Okay. So when in doubt, always check your answer. And keep checking it as you do it in the first place. That's always a good idea as well. But in the end, you can always check your answer in different ways like this. It's just a different calculation than what I was expecting. That's kind of I thought for a second I might be wrong. But it's okay. All right. Now then, another thing you can do is to derive the equation from a graph. So here's number 6, try number 6. I would point out, though, that in the book, this example that's associated with this try it question looks like it's a little bit off. So unfortunately, the book sometimes shows you graphs which do not correspond with what's written there. The numbers in the graph look different from what they're actually writing down. So I suspect there was some edits needed there which were perhaps missed, unfortunately. So I'm just going to write down what I see. And anyway, I've seen this before in the book, so it's not like it's there are other places I think where I've seen this as well. Okay, so try number 6. You have a function which is like this. So here's, let's say, 1, 2, 3, 4. And between 1 and 2, on the y-axis, it goes through. They give you 0 and the square root of 2. The square root of 2 is about 1.4. 1.41. So it's going through about halfway between 1 and 2 like that. And then from the graph at 1, x equals 1, the value of y is just a little bit above 2, it looks like to me. And then at the value 2, it's right about the value 3. And then at 3, it's above 4. Okay, so the slope is gradually increasing here. At minus 1, it looks like it's right above plus, y is right above plus 1. And at minus 2, it's right below plus 1. So the graph looks something like this. I'm trying to draw it smoothly and without any funny changes. This should probably be just right through smooth like that. Okay, so the question is, from the graph, can you determine what the values of A and B are? Okay, so they recommend that if you know the intersection point and that here is given, then you could use that right away to determine what A is. Okay, because A, as it turns out, is just the y-intercept. When you plug in x equals 0, this part becomes 1, and you just get y equals A. So the y-intercept A, you can right away write down as the square root of 2, or 1.41. All right. Then I'll use the square root of 2 just to give you an exact expression before approximating, before using a calculator. Okay, and then I'll take the point at x equals 2, and it's about y equals 3, let's say. So I couldn't really distinguish that y was any much different than just 3. So I'll use that value. So I plug in x equals 2 here into the original formula. I get the square root of A times B squared is equal to 3. So now I can easily solve for that. And I get B is equal to the square root of 3 over the fourth root of 2. Okay, and I don't know, I didn't calculate that, but I mean, I could just write that down. I could use those values. Okay, so I'd say that those are pretty close to what the correct answer should be. In a later chapter, the book deals with how to do approximations of several points in a curve, and you use a calculator to do exponential regression. And we won't do that for this class, but just to let you know, it can be done, just like you would do linear regression or polynomial regression using a calculator. You can use graphing calculators for that. Okay, now I want to talk about another application which is very important, and that's interest. Compound interest. Okay, so compound interest is to be distinguished from simple interest by, well, we'll first define simple interest. And then it's easy to see how compound interest is different. So simple interest is you take a fixed amount of money and you have a % rate of growth on that. And so you say put this amount of money in the simple interest account for 5 years, and every year you add a certain percentage of the original starting amount to the principal. So the principal is what you start with. you have an interest rate R. Okay. And then you after 1 year you multiply, you add this rate of growth, R times P, to the original principal. Okay, so you're starting with the principal, you add, after 1 year, R times P to that, and so you factor out the P, use the distributive law, and you get 1 plus R times P. Okay? That's after 1 year. All right. If you do this for a number of years, then you're simply adding the same quantity to the original principal. Remember, this is just simple interest. It's not compounded. So you take the number of years. Let's use a different value, T. T usually stands for the time in years. So here it's just 1. So you take that same added amount, you multiply it by T, and then you add it. So using distributive again, you take P outside, and it's 1 plus T times R. Okay, so that's what simple interest is. And so there are certain accounts which use that. Now, compound interest, it's sort of dealing with the actual money that you have in the account. So in compound interest, you make the money for a year, you add it to the original amount, and you get, so after 1 year you get this expression. After a second year, so t equals 2, you start with this, considering that as your principal now, your new principal amount, and you take R% of it and add it to that principal again. So that corresponds to simply multiplying that whole thing by the same factor, 1 plus R, which corresponds to multiplying the original principal that you started with at t equals 0. That's what that corresponds to, by 1 plus R squared. Okay? So if you do this after t years, you see that you just get the formula P times 1 plus R to the power t. Okay, so see, that's different from this one. This is going to be a linear function of t. This is an exponential function of t, which means that this is really the way to go. Compound interest will always give you, in the long run, a much greater growth rate. It'll give you growth, exponential growth rather than linear growth. So it'll always eventually beat that. Okay. Now, the second thing is, can we do any better? And yes, we can. Can we do better than compound interest? The answer is yes, we can, by shortening the time interval after which you compound the interest. So R will always be an annual growth rate. It's called the nominal annual growth rate. Annual interest rate, sorry. All right, so that's what you would get, the percent that you would add to the principal after 1 year, if that's all the compounding you did. You just did one compound addition, or one addition to your account every year. Now, if you did 2 additions per year, then the way that's done is you would take the nominal interest rate, divide by 2, and then take the percent after half a year and add it to the principal. All right? So you have this new number here called n. N is the number of periods per year number of compounding periods per year. Okay, so I'm taking the case where n is 2. So that's called semi-annual compounding. Okay, so now you take half of the interest rate over the first half of the year, and then you compound it twice during that year. So use that same factor and then square it. And this will be A1 after 1 year. This will be the amount after 1 year. If you did this for several years, then you simply multiply, you'll be taking this whole factor here, multiplying, or raising that to the new number of years t, and so this will become, using the rules for exponentials, you just multiply the t and the exponent there. Okay, so that's when n equals 2. In general, if you take n periods, you divide your year into n periods, and each period you compound with, effectively, the interest rate is r over n. Okay, so you take this interest rate, this is 1 year, divide it by n, and you take n compoundings of that interest, of that whole amount in that 1 year. So you have to multiply the original principal by the 1 plus r over n to the power n. So it's just like this, except I replace 2 by n. Okay, so if you make n bigger, in general, you'll get more amount after 1 year. And that's how you compare the effectiveness of each of these methods. You just compare it after 1 year. So this is the least of all. This is better, and this, as n gets bigger and bigger, it gets better and better. All right. Now finally, the best you can do using compounding is called continuously compounded interest. So that's where you're compounding every second. Now you probably don't actually do that. Not even second. I mean every microsecond. Well, it's continuously. So that just means n goes off to infinity. The number of periods gets so large that it doesn't really matter in the final amount. It's going to reach its maximum, as close as possible to the maximum amount that you can get. This is continuously compounded interest. Now, surprisingly, the formula is quite simple for continuously compounded interest. Oh, I forgot to mention, when you want to replace this by t here, you just put a t in there. So this is what the formula becomes if you put it over t years. You just take the whole factor raised to the power t, and so it just gets multiplied in the exponent there. So continuously compounded interest, then, is you let n go to infinity. Now, the way to get the formula is, it turns out that this number here, put a 1 in here, 1 plus 1 over n to the power n. So if n is the same in both cases. If you calculate this, it turns out this goes to the number I mentioned before, Euler's E, which again is 2.718, etc. All right. So the greatest this factor what happens is, if you put the rate in, like this, that goes to e to the power r. The exponential evaluated at the interest rate. The percent, it's not expressed as percent here, but as a decimal. The rate is then going to be, whatever, if it's 6%, then this will be a 0.06. So this is over 1 year. This is the factor that you would multiply the principal by to get the amount for continuously compounded interest. And if you do it over t years, keep on going, then raising this factor to the power t is the same as multiplying r by t. So you just get the principal times e to the r times t. Okay, so this is a formula for, again, continuously compounded interest starting with the principal p, a rate of interest r, again, it's the nominal annual interest rate. The actual interest rate is really this factor here. And anyway, it's related to this factor. This factor can be expressed as an effective interest rate of 1 plus r prime. That's over however many years. So that's not usually what you talk about when you talk about the interest rate. Usually you mean this, the nominal interest rate. And but the effective one can be quite a bit larger, but there's a limit to it. It only goes up to this continuously compounded thing. All right. So that sort of summarizes the best you can do using continuously compounded interest in terms of investment and so on. Okay. Now, I think we're probably, I don't want to go too much over time here. So where we are. Okay, so I'm already an hour and a half. Okay, so now I'm going to kind of skip some of the examples for now, but I talked about reflections and so stretching and shifting for now earlier. So at this point, I wanted to at least introduce exponential functions and do a few simple examples to try to wrap up this lecture. Okay. So this is now in section 6.3, logarithmic functions. Okay, so remember what I said last time, that the logarithm functions are the inverses of the exponential functions. So what we write is log base b, y is equal to log base b of x. And what we mean by that is it's the reverse of what we mean by the exponential function. We ask the question, given a value of x, we start with a value of x, what power do I have to raise b to get x? And that answer will be y. So y is the power I need to raise b to get x. Okay, and writing that out, it means b to the power y is equal to x. Okay, so this is the definition of the function. Given an x, that's actually going to be the final value of an exponential operation here. Right? Starting with y, I would raise b to the power y, and then that would give me x. But now I'm starting with x, and I want to get y. So it's, another way of saying it is I want to, if I'm given the value of the base here, b is always given, and I'm given a value of x here, then solve for y. And the answer is this logarithm function. Okay, so this equation is defined by this exponential equivalent equation, equivalent exponential equation, or the equivalent exponential form. All right, so let's see how that works. Let's see some examples. And we'll just go from one form to the other to see how these work. Okay, so if I have a simple one, let's say 2 to the power 2 is 4. 2 squared is equal to 4. Right? 2 times 2 is 4. So that's the exponential form. What is the equivalent logarithmic form? Okay, well, what I have to say then is a log base 2, so that's my base 2, you have to identify that. That's the same in both expressions. Log base 2 of 4, that's the final answer, is equal to 2, because I have to raise 2 to the power 2 to get 4. Okay, let's do another one. 2 cubed is equal to 8. Log base 2, again, the same base as before. Now raised to the power 3, so that's my final. So you just switch the x, you take the x that's going into the function here, and you make that the final result here. And you take the y, the final result here, you make that thing that goes into the function here. Okay, so I just sort of switch them like that. Switch them like that. Okay, and you can keep on going. Let's go one lower. 2 to the 1 is equal to 2. Right, that's even simpler than this one. Well, the way you'd say it is log base 2. 2 is 1. Now it's another simple one. 2 to the 0 is equal to 1. That's always true, so here it becomes log base 2 of 1 is 0. In both these cases, I'm switching the x and the y around, and the x value goes here is the new y value, the old y value is now the new x value. Okay, so that it just corresponds to, remember when you solve for the inverse function, you have to interchange x and y and then solve for y. All right, some other examples. Let's try log base 2/5 of 1 over 5. What should that be? Actually, let's make it a bit simpler for now. I'll modify it later. Okay, let's first try 5/25. Okay, so this is evaluating things now. What would I have to write down so that this would be true? Okay, well I write down my exponential version. It's going to be 25 is equal to 5 to the power what? What goes there? Well, I can easily see that should be squared. 5 squared, so that should be a 2 right there. So this should be 2. Okay. So if you can't figure out what the logarithm is directly, it might be hard. Just you write down the exponential form and then put the y right there. Remember, we were solving for y here. Okay. And then just see what it should be. So another one would be log base 5 of 125. So you can easily see that, again, I have to raise 5 to the power of what to get 125, and it's going to be 3. All right. Now, a trickier one. How do we evaluate this one? Log base 1 over 5 of, let's say, 25. Or let's first of all start with 5. What's the log base 1 over 5 of 5 going to be? So again, I have to raise, what power do I have to raise 1 over 5 to get 5? Let's put a y in there, just to show you how it works. So I want to solve for y here. I can easily just look at this and see, oh, if I just raised this to the power of minus 1, in other words, take the reciprocal, then I get back 5. So that enables me to solve and find y. If I put a 25 in there, then what do I get? Instead of 5, log base 5, sorry, log base 1 over 5 of 25. Right, so what should y be here? Well, now I have to take minus 1 and then also square it. So that means y is minus 2. Okay, how about a little bit trickier here? How about log base 25 of 5? What should that be? Log base 25 of 5. So what power do I have to raise 5 to get 25? Sorry, other way around. What power do I have to raise 25 to get 5? Well, the answer is, this is going to have to be the square root of 25, but we know from Math 101 that the square root can be represented by raising something to the power of 1/2. So y has to be 1/2. And then when I multiply 25 by 25 to the 1/2 times 25 to the 1/2, that's going to be 25 to the 1/2 plus 1/2 is 1. So that's why this represents the square root. When I multiply by itself, I get just the original number back. So that means that the square root, or 25 to the 1/2 must be 5. So that's why the answer should be 1/2. How about a log of 125 of 5? Log base 125 of 5. Okay, what would you guess? If you guess 1/3, you're correct. Why? Because 125 raised to the power of 1/3, that means taking the cube root of 125 will give me 5. So that's the equivalent exponential form. Okay, so let's figure some other ones out. If you had you can now do this with a whole number of things here. Well, let's say 6 minus 1 is 1/6. Okay, so what is the equivalent logarithmic form of this? This just means take a reciprocal of 6 and get 1/6. So the equivalent thing will be, this means equivalent to log base 6 of 1/6 is minus 1. So this, again, gets switched around. And now the y becomes the x here, and the old x here becomes the y here. All right, so you can go back and forth between these just by remembering the basic equivalent exponential relation for a logarithmic one. Can we have this? The answer is no. This does not exist. Because the base has to always be positive and not equal to 1. So, no answer. Not defined. So anyway, that's at least a starting introduction to logarithms. I might mention, by the way, that when you deal with log base 10, that just is written as log by itself. Hopefully there's no problem with that. You have to always read in the context. In worst case, just check the book to see what is defined if you just see that log by itself without any base. But usually in this class, if it doesn't have a base, then it will assume to be base 10. And there's another one, log base e, is usually written ln, and you pronounce that ln. Ln, and that simply stands for natural logarithm. Okay, so the ln function will be y is equal to ln of x. That's equivalent to x is equal to e to the y. All right. So it's the inverse function of the exponential function where the base is Euler's number. And the natural logarithm function, and both the exponential and the natural logarithm functions, have very wide use. They're very important in especially calculus and further on physics as well. Okay. It has special properties that make it kind of unique and different from all other logarithms. So the base e is somehow quite special and important in mathematics. Okay, so an example here would be log base 10 of 1,000,000. What is that? And now don't say 10 to the power of 1,000,000. It's a huge, huge number, and that's not the answer. That would be the answer for the exponential function, right? But this is the other way. So you ask this question, what power do you have to raise 10 to get 1,000,000? And the answer is simply 6. So it's much smaller. So logarithms will take you, as we saw, exponential functions take you from reasonably small numbers to very large numbers. And the logarithm functions will take you from very large numbers and describe them by very small numbers. So logarithms are especially useful in chemistry and physics, where you are sometimes dealing with huge numbers of particles, and then it becomes very, very handy. In fact, the notion of entropy in physics is you need to describe it in terms of the logarithm of the number of accessible states of the system, which can be extremely large. And even then, it's just proportional to that number. You have to give it units like an energy, which numbers by themselves don't have. Okay, so now I'll deal with the other examples next time, but this seems to be a good time to stop. Okay, so have a good day, Hudofus, and take care.